So after our panel of experts in algorithms, now we have a session about hardware, which is essentially how to build a quantum computer. Our first speaker today is Thaddeus. He's a world expert in quantum control. He's got more than 15 years experience in the field, and he's interested in networks and ion traps as well. So please start.
Thank you. And thanks to the organizers of this conference for inviting me. I've been very much enjoying it, and I'll be talking today about semiconductor qubits for quantum networks. Anybody see it? There it is. This is a picture of where I work. This is HRL Laboratories in Malibu. I know many of you may not have heard of HRL Laboratories, so I thought I'd say a couple words about it. This is the location where, in 1960, the very first laser was demonstrated. It's an apt thing to point out, not only so that you know something about where I'm coming from, but I would remind you that the laser, when it was invented at that time, was something that physicists really wanted to see, but it kind of didn't have known applications. Someday we might be able to use lasers for this, someday we might be able to use lasers for that, and these days we do use lasers for this and that, so it helps with perspective in a field like this. HRL is a company of about 400 people. It specializes in quantum electronics, microelectronics, and novel forms of computing, so quantum information technology seems like a good thing for this laboratory to be working on. I'll be giving a talk that looks both backwards and forwards. Backwards into what has been demonstrated in semiconductor qubits in recent years, as well as what ways we can put them together in the future. So I'll be going through things kind of quickly in this talk. If you want more details, I recommend you look at this paper in which this talk is based. It was recently published, and between the 30 pages of this paper and its 100 references, you'll find all the details you need. So here's the takeaway. A lot of things now work separately in different semiconductor systems. Semiconductor quantum dots can make very high-speed, deterministic single photon sources. You can entangle the spin of electrons trapped in quantum dots with photons. That works. You can have quantum memories that live for quite long times in semiconductor dots. You can quickly initialize, control, and read out qubits with lasers in nanosecond or even sub-nanosecond timescales. You can do the same thing with electrical gate voltages. And you can couple these qubits via capacitive interactions. And all these things have been shown to work separately. The takeaway to this message is that making them all work together is not only possible, but also useful. What it's useful for is this problem of quantum communication and quantum networks. There'll be another session on quantum communication and quantum networks later, but I do want to talk a little bit about networks in this talk in order to motivate the hardware that I want to discuss. Very briefly, the good things about quantum networks is that there are applications for them in metrology, in distributed sensing, in cryptography certainly, and in computing. Of course, a very well-known application is using networks to increase the distance and speed of quantum key distribution, giving you distributed, future-proof public channel cryptography. Of course, the bad of quantum networks is that ultimately, they rely on single photon transmission, and single photons get lost on the way from here to there, and that absolutely requires forms of error correction, and speed is going to drop very quickly as you move transmitters and receivers away from one another. The ugly of quantum networks is that they're a little bit hard to market these days. That's because most of the applications that are envisioned have very good classical counterparts, so it'll be some time before they're actually able to compete with what currently exists. And to really make the kind of network that I envision, you really require fairly expensive devices that use cryogenics or high vacuum or something in a relatively dense network, or putting these things on satellites. And those are, of course, challenging technical issues that I won't address any further. Semiconductor qubits, I also want to give a good and bad and ugly of these in general. The good, which I'm sure you've all heard before, but it's worth hearing again and again and again, the real reason to go to semiconductors is engineering, engineering, engineering. There's lots of things you can do with semiconductors. You can engineer the band gap. You can engineer the G factor. You can do the best lithography mankind knows how to do, MEMS, et cetera, et cetera. Right? It all comes down to there being existing mature industrial materials and existing mature industrial tools. And this is good enough to warrant against the bad, which is that you always have to deal with the fact that semiconductor qubits are constantly battling with disorder, inhomogeneity, the need to control single electrons over very small scales, charge noise, nuclear spins, etc. And the ugly of semiconductor qubits, which I won't address, but it should be in the back of your mind, is that everything I'll discuss does require cryogenics. Okay, so this talk, I will start by addressing the bad of each of these components. First of all, the bad of quantum networks. We need to figure out how to make them faster, how to make them more scalable. I'll talk about that. And then I'll address the experiments that have addressed those bad aspects of semiconductors and shown how they can all be overcome. And then I'll return to this proposal for loading a register of semiconductor qubits optically. Okay, so let's start with brief comments about quantum networks. Quantum networking, almost everything in quantum networking relies on this one primitive resource, which is, not surprisingly, quantum teleportation, right? It's this notion that this can be easily recognized by experts as a teleportation circuit. Here's your Bell state analysis. Here's some form of entangled pair generation. And the point is not just that this quantum state theta gets teleported from there to there. The point is that if these are single photons and this coincidence detection succeeds, it tells you not only how to recover the state, it also tells you that this photon and this photon made it from its source to its destination, right? That's this basic primitive. It appears all over the place in many, many papers. This paper's from 2002 from Peter, but it's in almost anything, and there are many devices that are based upon it. They're so-called quantum relays, which basically is this primitive. There's quantum relays that have buffers, i.e. you add memory to this so that you hold photons until you see a success. There's quantum repeaters, which include this primitive, plus a buffer, plus the ability to do some sort of error correction on the memory. Then there are quantum routers that have all of that, plus the ability to multiplex signals and route them from one place to another. I've just made up some symbols for these different things that I've stolen from Cisco, Cisco products, but just to indicate that this has become kind of an engineering problem. An example of how some of this engineering can be done, this is written up in this recent archive paper, right? A very canonical way to connect two quantum repeaters is to have this little device that entangles a spin to a photon, and it spits out these photons, and then you interfere these two photons at a beam splitter. When there's a double-click coincidence, you send back a success to this repeater, which does its thing, and back to this repeater that does this thing. And in this paper, this protocol is called meet in the middle, right? You can add to that another one of these sort of relay channels by basically putting an entangled photon source in between. This sends out entangled photons to both directions, and the same coincidence detection happens now twice. But the advantage here is that when this fails, when you don't get a double click, this repeater knows it right away and can immediately reset its qubits. And if you analyze how quickly you can generate entangled pairs in each of these two, you get a quadratic speedup by just inserting this entangled photon source, which is helpful in increasing the speed of entanglement distribution. Now, you may say, hey, wait a minute, you've cheated. You've taken a transmitter and receiver, and you've inserted a repeater-like thing in between them, and so of course you get a quadratic speedup. But again, this is an engineering problem, not a physics issue. This entangled photon source is a much, much cheaper device than this repeater. It doesn't involve memory. It doesn't involve any logic. It's just a fairly stupid and mature technology that just spits out entangled photons every 10 nanoseconds without any intelligence or feedback. And so it's a much cheaper thing to insert in between these two repeaters than a whole other repeater. So this kind of engineering trick can give you something like an order of magnitude speed up. Of course, it only really helps if you have a very fast reset time for the underlying physical device. Here I compare typical reset times for some hardwares that are being used, trapped ions, NV centers, and quantum dot devices. And for the most part, the speed up in generating entangled bits is dominated by the ultimate clock and refresh time of the hardware. That's the most important thing to optimize. And then once you've reached a certain speed threshold, these engineering optimizations can give you another order of magnitude or so of speed. So when it comes to actually engineering a network, I'm not saying this problem is solved, but what I am saying is that there is a lot of room for what is more traditionally called electrical engineering. There's a lot of room for taking these components as black boxes and putting them together in novel ways that increase the overall speed. So a quantum network is in general going to use many tools. There's one important lesson here, though, and that is that you can't just willy-nilly insert these fairly easy relay devices and expect to get any scalability of a quantum network. It's because, as we all know, everything that we make is flawed. Everything introduces errors, and it's not just photon loss, it's also errors in the actual encoded quantum information of the photons that make it through the network. So you absolutely need error correction. So you need a certain density of devices that actually do some form of error correction. There are two basic forms of error correction that people have explored for networks. One is purification, and one is quantum error correction. It's definitely worth studying these things more. I say here, like quantum computers, quantum networks will require error correction to be interesting for any real application. If you're at a distance where you don't need error correction, you're also at a distance where you don't need quantum communication. That's my claim. So this is pretty important. Purification is slow because it requires a two-way reconciliation, but it is fairly robust to errors and can be robust to very high rates of loss. These are some papers which do some analysis of purification scheduling. The use of quantum error correction, surface codes, and all that has been studied more recently and by a number of groups around the world. This is great because you can get very high-speed communication with these devices, but you need a lot of qubits, and you need loss rates fundamentally less than 50%, and usually much less than that in order for it to work. Whatever your scheme ends up being, quantum repeaters have to support multi-qubit logic to do either of these. Okay, so that's all I want to say about quantum networks in this talk. The takeaways here are that quantum repeater devices have to support a rapid refresh rate in order to be practical. This is a challenge for trapped ions, which are necessarily slower, and it's a good feature for self-assembled quantum dots, which I'll talk about next. But quantum repeater devices also have to support multi-qubit logic. This is a challenge for NV Diamond. It's also a challenge for those self-assembled quantum dots, and this is why we need to move to something else, and for that I'll motivate gated semiconductor quantum dot arrays. So quantum repeater devices can be made in semiconductors if we can combine self-assembled quantum dots and quantum dot arrays. That's the motivation for this device I want to propose. The next part of this talk, I want to talk about the experiments that support the proposal. So let me start with self-assembled quantum dots, which are there in order to make a strong optical interface. Okay, many people in the world are working on self-assembled quantum dots. They're worked on here, they're worked on there, they're worked on everywhere. And for very good reasons. One thing that can be done, and again, this comes down to the engineerability of semiconductors. Well, if you don't know what self-assembled quantum dots are, they're strain-grown dots. So these little blobs here are blobs of indium arsenide that have been deposited on gallium arsenide. And just due to strain, they make these little droplets. This is an AFM image of those droplets. So they're random. They're randomly placed. Although, because they are driven by strain, if you make little divots in the underlying gallium arsenide, they will assemble right at those divots. So you can put them where you want them, and this was done at the University of Würzburg in this image. And you can put them inside of cavities. This is a DBR micropillar cavity, a waveguide cavity, a microdisc. This particular result from a couple years ago is in a photonic crystal waveguide where they're able to get high 90% output coupling efficiency of single photons. So there are many options for getting photons efficiently out of these quantum dots. There are also many options for control. If there's a single electron in those quantum dots, which is fairly easy to put inside them, you can very rapidly manipulate that single electron spin, initialize it, and control it using either continuous wave lasers or picosecond pulses. You can entangle this spin to the photon that comes out of these microcavity structures. This is a fairly complicated setup that was put together at Stanford to demonstrate this. I guess I'll highlight one aspect of this setup that's important, which is that it did use nonlinear optics. Nonlinear optics gets used for many things in quantum dot architectures. It can be used to convert the wavelength to telecom for that purpose. It can be used to upconvert the wavelength of light to some place where you have a convenient detector. In this case, it was actually down-converting. We were using one of these superconducting photodetectors, which we may hear about in the next talk. So it wasn't really about getting the right wavelength for that. What it was more about was time resolution, because this nonlinear medium would only transmit a photon at 1560 nanometers if the photon overlapped with an 8 picosecond pulse pump source, and that basically puts an 8 picosecond timing filter, which was important for demonstrating the spin photon entanglement. Again, for more details, you can either look at these papers or look at these lecture notes or read the paper I put at the beginning of this talk. I know this is a little fast, but I do have a lot to cover here. For one perspective, self-assembled dots, they're great. People are working on them. They can do everything, so can we go all the way with self-assembled dots? And this is certainly a question I tried to answer for many years. I even co-published this paper in Physical Review X in 2012, where we imagined a whole quantum computer of self-assembled quantum dots in an extended two-dimensional architecture. And the really nice thing about this is that there's no wires, or a very small amount of wires. And wiring is a big problem in quantum computing architecture. What you do have to do is distribute lasers, but using a combination of MEMS and these phase shift masks, you can distribute lasers anywhere. That's not the problem in the system. So it's almost there as a really interesting technology. The problem is that the proposal in that paper for how to do 2-qubit gates, and I can be critical of it because I wrote it, it just isn't going to work. 2-qubit gates can be done in self-assembled quantum dots by stacking them. Work at NRL and ETH and other places use quantum dot molecules. So this is a case where you vertically stack quantum dots. Again, they're nucleated by strain, so one layer of quantum dots can nucleate the next layer. So it's actually relatively easy to stack 2 or 3 or 4 right on top of one another. And then there's a very small 10 nanometer or so barrier between them, and there's tunneling, and so there's an exchange interaction. And that can be used as a basis for controlled logic. It can also be used to define singlet-triplet qubits, which I'll talk about in more detail later. This is an example of looking at Ramsey fringes of singlet-triplet qubits. You can either interpret this as a single singlet-triplet qubit, or you can interpret it as a 2-qubit exchange gate between 2 electron spins. Either way, a lot of possibilities open up for you when you stack dots like this. If you do imagine a singlet-triplet manifold, you're immune to global magnetic field fluctuations, and you can bias it to be immune to electric field fluctuations. I'll talk about that in a little bit further. And you can tune the dipole coupling, which is going to be important for what follows. So this is all I'm going to say about self-assembled quantum dots at this time. Some takeaways here. Self-assembled dots are great. They make good singlet-triplet qubits. They have very strong optical cross-sections, but they do have problems. One problem is they're implemented in 3-5 semiconductors, and there are nuclei everywhere. And this limits the T2. This limits the coherence time to microseconds. And also, I know how to stack 2 of them, maybe 3, maybe 4, but you can't keep going. You just can't. So there's no clear path to larger arrays. Gated quantum dots, which will be the next part of my talk, has a clear path to larger arrays and can have a T2 time even in the midst of all of these nuclei in gallium arsenide of milliseconds. But it has a challenging optical interface, which is what motivates linking them up. Now, gated quantum dots aren't perfect. There's a lot of problems to deal with here, which I'll now talk about. As I mentioned, one is disorder, and for that I'll address this undoped accumulation mode of making quantum dots, which has really been HRL's focus over the past few years. I'll address how to deal with charge noise, which is still the dominating error, and I'll address how to deal with nuclear noise, either via isotopic enhancement or dynamical decoupling. So that brings me to the next part of this talk, electrical quantum dots. Okay, there are many ways to make dots that you can control electrically, and fortunately, you're going to hear about several others at this conference. Just to put what I'm talking about in perspective, I think you'll hear from Andrea Morello tomorrow about the single donor. Right? The nice thing about a single donor in a semiconductor is that you get confinement of a single electron without using any gates, really. It just confines at low temperature and thermal equilibrium. You then add gates, of course, for control and measurement. So this is a very nice and very elegant system that was proposed many years ago. Multi-qubit coupling is possible, and Andrea will undoubtedly talk about some great ideas for how to do it, but it is definitely a challenge in this system. Andrew Zurach will talk about metal oxide semiconductor quantum dots. What's great about these is that they're very similar to commercial transistors, right? It's MOS, as in classical CMOS. And of course, the danger here is that your wave function for your confined electrons is smushed against this amorphous oxide, and you may have to worry about disorder in that barrier. Of course, as Andrew will tell you about, you can get over that and still do some amazing things in the system. So the jury's still out as to what system will proceed in the future. But at HRL, we have focused on the heterostructure approach. And the reason we focus on it is because there's a cleaner barrier between your wave function and your oxide and gate stack. It's a semiconductor barrier. You can make these sorts of heterostructures with molecular beam epitaxy or chemical vapor deposition. You can make them in silicon germanium, or in gallium arsenide, aluminum gallium arsenide. And HRL and many other groups in the world have done this now many times. I just want to briefly tell a story that most of the early designs for 2-DEG-based quantum dots use this modulation doping. So there's a doped layer that populates a quantum well. And that leads to some disorder, because there's disorder due to those dopants. And an important development recently has been getting rid of those dopants and moving to this so-called accumulation mode design. Accumulation mode is useful for two reasons. One is because it allows you to work in this dopant-free, lower disorder mode, but also it makes devices more tunable. And that's actually a critical engineering consideration. Here's what I mean by that. So depletion mode is sort of the old way of operating. That means that in depletion mode, you have this 2-DEG, a two-dimensional electron gas, where there's electrons all over in this quantum well, and you define qubits by depleting electrons away with a negative bias on gates, push away everything except for the qubit electron that's left behind. And of course that works, but it's got an issue, which is that if you ask, how are you controlling this single electron? Well, in this picture, it's being controlled by both of these gates. And in reality, you don't have two gates, you have like a dozen gates. And it means that electron is really being controlled by all dozen of those gates. And it makes it a tuning challenge. In contrast, accumulation mode, you positively bias these gates, and you essentially trap a single electron predominantly under one single gate. And in systems with high disorder, such as silicon, the disorder isn't that much higher, it's that the effective mass is higher, so you're more sensitive to disorder. Moving to this mode has been critical. By the way, a system that I expect to have disorder as well is a gallium arsenide system in which you have, for some reason, grown a layer of self-assembled quantum dots close to your quantum well. So although you don't necessarily need this mode for gallium arsenide-based quantum dots, you will for the hybrid optical device that I'll get to at the end of the talk again. So this has been the basis of HRL's ability to increase the yield of gated semiconductor dots. If you want to read more about this, you can either look at this APL letter, but what I really recommend is this perspective written by Andrea Morello, which is much better written than the introduction of this paper. Thank you for that, Andrea. Really, this is a story that started at UNSW about 10 years ago, so it's really been instrumental in making these gated dots work. Okay, so I don't want to talk anymore about how the device is made, but rather how we control it. So this is a scanning electron micrograph of the HRL triple dot. And this is sort of a cartoon of how you can interpret this thing. This looks a little bit like a dental x-ray, right? But what these things are, they're overlapping metal gates, which are holding these electrons in this potential. This dot over here, the so-called M dot, is a so-called measure dot. Essentially, we measure by looking at current from a source, which is the electrons under some bath, to a drain, which is electrons under another bath. We have controllable tunneling between them with these so-called Z gates. And then this M dot via Coulomb blockade can block or pass electrons depending on the energy level of that dot, which is, of course, controlled by whether there are electrons under these so-called P gates. And that's the basis for measurement in this system. It allows you to tell whether you have a single charge or two charges or three charges under any given dot. Also, we can initialize via tunneling, right? These T-gates are there in order to have controllable tunneling by many orders of magnitude from one of these baths into these dots so that you can load one in quickly, very quickly, and then raise that tunnel barrier so that it's completely stable. And that can all be done very, very fast. So the control bandwidth is from DC to about 1 gigahertz, and as I'll show, you can completely control this thing as a qubit without using lasers, without the need for microwaves, without the need for magnetic field gradients or anything. You just need electrical gates. Okay, so the basis for all control in these gated dots is tunneling. The canonical way of operating a double dot is you have 2 electrons in 2 dots, and this is a diagram that shows the energy levels as a function of detuning. That is the relative chemical potential of one gate-induced potential to the next, right? So over here, this is a much lower energy, so the 2-electron state is the ground state. Over here, the other 2-electron state is the ground state, and then because of quantum tunneling from one potential well to the other, you have this anti-crossing to the 1-1 state. The qubit is defined by spin, so because these 2-electron states are necessarily spatially symmetric, they have to have an anti-symmetric spin, so these correspond to the singlet, whereas the triplet is a symmetric spin state, and it is restricted from tunneling, so-called polyblockade. So as a result, there's an energy difference between the singlet and triplet, and that energy difference is ultimately the basis of control. We can change a voltage, which is really what this axis corresponds to, and as a function of that voltage, the singlet to triplet energy changes. That's known as kinetic exchange. And that provides rotation relative of a singlet relative to a triplet, which is envisioned as a Z rotation in the Bloch sphere of that qubit. If you only had Z rotations, it would be a very, very boring qubit, right? And I did argue that we can control things with only this one primitive, so that's why we moved to a triple dot and 3 electrons. So I've said that double dot exchange rotates a singlet triplet qubit around the Z-axis, but to get full Bloch sphere control, we need some additional axis. And adding a 3rd electron gives us exactly that. So if you imagine detuning dots 1 and 2, as I said, that corresponds to a Z rotation. And what happens if you detune dots 2 and 3? Well, what that's going to do is lower the energy of the singlet for dots 2 and 3, and the singlet is not orthogonal to the 2-3 singlet is not orthogonal to the 1-2 singlet. In fact, it mixes into it with some angle, which is given by Clebsch-Gordan coefficients, and if you do the math, it corresponds to a rotation in this singlet triplet Bloch sphere by 120 degrees. So it's a rotation around this so-called n-axis. And so you can get anywhere you want on the Bloch sphere by doing alternating rotations about z and n. And mathematically, it was proven in the 1970s that you can do absolutely any unitary operation you want for a single qubit up to an overall phase with at most 4 pulses, that is 4 alternating rotations between the two. You can even get the overall phase relative to other angular momentum subspaces with 5 pulses. You might also ask, hey, so we know that these 2 dots are in this singlet triplet basis, so we know what's happening with those spins. What happened to the 3rd spin? Well, what's that? It turns out not to matter. It can be up, it can be down. It's a so-called gauge freedom of the system. Okay, so we know how to construct arbitrary rotations, and we've recently done this at HRL in a triple dot device. So let me show you an experimental result from that device that I showed an image of earlier. Here's how this experiment works. The qubit is initialized in a singlet, meaning along the z-axis. A pi pulse around the n-axis is done by biasing where the 3rd electron is in its ground state. And that takes you down to some line of latitude by rotation around this n-axis. And then we bias to some voltage, which can either correspond to a z rotation or an n rotation, depending on how close you are to the 201 charge state or the 102 charge state. And then you do a pi pulse to get you either back up to the z-axis or not. That's the basis of fringes. And you can see just on one voltage axis here, which you'll notice is only being changed by order of tens of millivolts, and time on this axis that you see fringes either around the n-axis or around the z-axis. And that shows that you can do both. And you've got a decent number of fringes. There are a few features of note in this data. One, you see this sort of streakiness that's coming in. That's actually the effect of the nuclear spins. This happened to have been done in an 800 ppm isotopically purified sample, so those streaks only start appearing on the order of 3 microseconds. That's the real advantage and reason to work in silicon. You'll also see that at the higher speeds, where the fringes are fast, you see fewer fringes, and that's due to charge noise. So charge noise is the big problem with operating these things quickly, and I'll address that. One quick diversion, which is people want to know, how do you take this triple dot qubit and do multi-qubit logic with it? This is obviously an important thing. And the answer is just more of the same stuff, right? So if you have 3 dots making 1 qubit, 6 dots make 2, and this sequence of only pairwise exchanges accomplishes a controlled NOT gate in the singlet triplet subspaces of the 2 qubits. It happens to be 22 pulses. We can now, this was actually found via computer searching, but we can now derive this from first principles. You might say, hey, why is it so complicated to make a controlled NOT gate between these 2 qubits? Well, that's just the way the math works out, but it's not really that complicated. In fact, from an engineering point of view, it's extremely simple, because all I have to optimize is this one type of interaction, just exchange between any pair of dots. That's the only thing in my whole array that I have to do well, and then I just paste those things together in smart ways. Just like, you know, if you make a transistor very well in classical electronics and then you want to make an XOR logic gate, you're going to be putting a whole bunch of transistors together. That's the principle here. Okay, so let me address this question of charge noise, because it is a limiting thing for these gated quantum dots. The way charge noise manifests is, remember, our control is, we have a voltage here, and this J changes as we change that voltage. We're obviously going to get, what charge noise does is it looks like a random voltage. So that is going to make more noise when the slope of J relative to voltage, dJ dV, is higher. And anybody looking at this diagram can see that there's this spot here. So the plot I showed last operated in this high detuning regime where the slope is actually quite high. But you'll note that there's this region here where that derivative, dJ dV, is 0. But that's also where operation is the slowest. The question is, can you get high-speed operation while still working in this regime where we have a small value of dJ dV? And that is possible. The principle, the physical principle, is you want to be biased at this symmetric operating point, and you want to just quickly lower this barrier. And because of essentially disorder in the system, that is not easy to do. It means for all of the gates, and if you remember that diagram I showed you about 5 gates controlling each electron, you need to be able to pulse on all of those gates quickly in a synchronous way. But once you get that set up, you can do some nice tricks, and this is what we most recently published in this paper that appeared about a few weeks ago. Essentially, we pulse on all of those gates, and this is a diagram of those Rabi fringes as a function of both the detuning voltage and with this overlapping exchange gate voltage that occurs between the P gates. And you get this, what we call a fingerprint pattern, and you note that there's more fringes along this direction, which is the symmetric operating direction, than there is along this detuning direction. So this is doing exactly this biasing while opening up the tunnel barrier. So we call this the symmetric axis. You can show that it actually gives you better resilience to charge noise by, say, looking at one of these fringes that corresponds to a constant rate of rotation J. This one happens to be 160 megahertz. And at each point here, we look at time domain Rabi fringes and ask, how many fringes do we see before you decay to 1 over E? And of course, right here at the symmetric axis, you see the most fringes for the highest fidelity. And this gives a substantial improvement in fidelity reduction due to charge noise. These results were done at HRL, and they were done in silicon, but there's nothing special about silicon for this charge noise mitigation. The same experiment was done by the Charlie Marcus and Ferdinand Clemeth group at MBI in Copenhagen. They observed a very similar number of fringes using almost exactly the same method. And the other thing they were able to do is, because you now have these very high fidelity exchange pulses, they were able to apply thousands of them in order to do dynamical decoupling. And that's important for gallium arsenide, again, because of nuclear spins now. There's all of these gallium spins and arsenic spins, and those cause magnetic dephasing, and you have to get rid of that effect. But if you've got good enough exchange pulses, dynamical decoupling will do that for you. So they were able to observe a T2 time of order of millisecond in gallium arsenide, which, by the way, is about the same as what we observe when we go through the trouble of isotopically purifying silicon germanium. I'll also mention that this symmetric operating point of reducing charge noise has been demonstrated in self-assembled quantum dots as well. It was done in about 2012 by Hitachi Momoglu at ETH. Essentially, he took one of these stacked self-assembled dot pairs, biased it at the same sweet spot of the singlet-triplet diagram, and showed via coherent population trapping that the coherence was extended from about 10 nanoseconds to 200 nanoseconds for T2 star. And that's, again, due to this resilience against charge noise. Okay, so I've now talked about optical quantum dots, electrical quantum dots, and hopefully motivated that we've made a lot of progress in the last few years in making these qubits actually work. And in the final 5 minutes here, I want to show how we can put them together in order to make an optically loaded memory. There are some ways that you could imagine adding optics to gated dots. For example, there's no reason you can't send a photon straight into a gated dot array. But and Seigo Tsuruta at University of Tokyo is doing exactly this. But you have a very small optical cross-section here, and there's not a good way to output a photon either. You can imagine direct tunneling between these kinds of dots, but the energy levels are really very different. I think the only smart way to do it is to use this capacitive coupling, which is basically two dots makes an electric dipole. That dipole can be thought of as creating a voltage on this other pair of dots, which of course modulates its exchange, and that's a so-called capacitive coupling. And recently, Amir Yacobi's group at Harvard showed how you can do a controlled phase gate between two laterally coupled gated quantum dot pairs in gallium arsenide. So the principle of this proposal is to do the same thing between gated quantum dots and self-assembled quantum dots, introduce this capacitive coupling, and in that way be able to move the entanglement of a single spin, which goes off into a quantum network, with this gated dot array, which we're able to scale up to things like error correction. We haven't built this device yet. We're in the modeling and simulation phase. This is what the stack would look like and the corresponding energy levels. As I mentioned, we have to worry about disorder between the self-assembled quantum dot strained layer and the hopefully high mobility quantum well. For this, we really appeal to this all-accumulation dopantless mode of operation. The critical figure of merit for this that we are so far answering by simulation is what is the strength of the capacitive coupling. If you imagine a poly-Z operator, which is the difference in singlet and triplet energies, and you work out the Hamiltonian, you do get this non-coupling, this coupling element. It depends on how you bias the singlet-triplet qubit, and it also depends on this constant delta, this dipole-dipole coupling. This bias is exactly this control parameter I've been talking about in the past. And this delta is, again, calculated with full three-dimensional Schrodinger-Poisson calculations. There's sort of a regime of distance between the self-assembled dots and the gated dots that's ideal with respect to tunneling. You want to be able to initialize the system by tunneling through that barrier, but you don't want it to be too fast because you want the system to be stable. So there's this sort of nice regime where that coupling constant looks like it's going to be about 500 microeV, which corresponds to a very fast operation time that will be slowed down by lateral misplacement between the self-assembled dot and the gated dot. That's what this calculation indicates, is how far off you can place your self-assembled dot pair relative to the gates in order to still get a coupling larger than about 10 microeV. So once you build this, there's a control sequence, which I'm not going to go through in detail now in the interest of time, but it's all using things that have been demonstrated before, fast nanosecond scale pulses on the optical dots, nanosecond scale electrical pulses on a buried triple dot, and you can show that this whole cycle time could be engineered to be less than 100 nanoseconds, which is important for these high-speed networks. Lightning fast, there are still problems. There's charge noise. The system I showed you to reduce charge noise actually also kills this capacitive coupling. AC gating can compensate for that. Nuclear noise, we have to figure out how to incorporate dynamical decoupling well. Spatial positioning, I've shown that it's possible, but I haven't actually engineered it into the system. Efficient outcoupling, this has been demonstrated for single dots, but not for this larger hybrid device. And improving the optical control fidelity is important as well. So with that, I'll acknowledge the team that has been working on this at HRL, the Quantum Communications Group, and take any questions. Thank you.
Time for a couple of questions. Over there.
Hey, Dr. Ladd, okay, so just start off with fabulous bit of work here. This is really impressive. Congratulations. But let me take this sort of a little step further here. Just ask you to sort of work from here out into the world of conjecture. Mm-hmm. And let's just say I'm some very wealthy megalomaniac, and I've just walked in and said, Dr. Ladd, I want you to build me a quantum internet. Now let's dispense with irritating questions like why. Let's just say I want to do this, and after you get up off the floor having, fallen down hysterically laughing, where would be the thing that you would think, boy, the thing that really worries me about doing that would be fill in the technological gap for me?
Well, the thing that worries me first is that I have to go to this megalomaniac and say, step one, I want you to build these repeater stations. Each one of them is going to have probably a cryo-free dill fridge, and I want you to place them every 100 kilometers or so over where you want the network. Done. Awesome. Okay, so you need to lay fiber between these repeaters. That's easy. Yeah, trivial. Okay. And you need energy going to those repeater stations.
I've got solar power.
You've got solar power. Great. Well, I also need a few years to solve these problems and get this control correct. So you're going to need to fund my lab to work on the composite pulses and dynamical decoupling. Yes, okay. And then I have to warn you that after we do all that, and after we have all that expenditure, I'm going to be able to give you absolutely future-proof secure keys, but it's going to be much slower than what you're used to on classical networks. It's, even after all the engineering we do and all the optimization, it's still going to be hard to send, say, a secure video over this network. So, you're going to have to be limited to secure SMS messages.
So then the question I would ask you then, I guess is where I'm going, is how could you, other than making duplication, how could you maybe think about speeding that up? And I'll allow you to do blue sky thinking, no one's going to repeat this.
Okay, well, the way to really speed it up is to move from a purification-based network to a quantum error correction-based network. And for that, the scale of the quantum repeaters is almost on the scale of a quantum computer. Not quite, because you don't need universal logic. You're only doing basically a surface code or similar code, which you don't have to worry about magic state distillation and all this sort of thing. So you're not actually making quantum computers, but you're making something fairly complicated and large, which is just going to take more engineering time. And I'm not going to allow you a density of 100 kilometers anymore. Now I need a density of 10 kilometers. So you still say done?
We have time for maybe another quick question. Back at the end.
So the first question was so interesting, I actually want to follow up on it. I want to challenge you even further. There's a proposal a few years ago by Gottesman, Croak, and Genevine to build optical telescopes that could essentially look at sunspots on distant galaxies. And they would do so by being separated by, say, the width of the solar system, and then using quantum repeaters to teleport light between the two receivers.
Yes.
We need 10 to the 11, yeah. So we need 10 to the 11 qubits per second to do that sort of thing. Is that just an engineering problem, or is that impossible?
Well, first of all, it's not impossible, but I'm not sure I believe the number 10 to 11 entangled bits per second. I think even if you ask Dan Gottesman, and I have asked Dan Gottesman, that's a very rough estimate, a very loose bound. I think there is room, as I've mentioned, there's room for engineering the network to speed it up relative to the existing speeds that known designs have. But I think there's also room for engineering a system like this wide baseline telescope application to reduce the needs of the entangled photons and still get the same spatial resolution. I can't be quantitative in that claim, but I don't think we're going to need to get to that level of speed to make that an interesting application.
Okay, let's thank Thaddeus again.